In October 2025, a team of researchers published a paper in Nature Astronomy that drew a direct line between chemicals detected inside Enceladus by a spacecraft that burned up inside Saturn's atmosphere 8 years ago and the chemistry of life on Earth. The molecules they identified in Cassini's archived data were esters and ethers, compounds that on this planet form the membranes of every living cell. Not simple space molecules, not building blocks in any vague metaphorical sense. Structural components of biology as we know it, confirmed as actively present in the ocean beneath the ice of a moon 900 million miles from Earth. The spacecraft that found them has been dead since September 2017. Its final signal reached Earth 83 minutes after the probe itself had already vaporized inside a planet's atmosphere, because that is how long light takes to travel from Saturn to here. And right now, in 2025 and 2026, the data it sent before that final silence is producing discoveries so unexpected, so fundamentally significant, that researchers are publishing papers describing what they are finding with words like simply phenomenal and the clearest signal yet. This is not a story about old photographs getting cleaned up with better software. This is a story about what was always hiding in the numbers, waiting for science to develop the understanding and the tools to read what was already there. Cassini was launched in October 1997 with a Huygens probe attached to its side. It spent 7 years crossing the solar system before arriving at Saturn in 2004, and what followed was 13 years of continuous discovery, 43,048 images, 294 orbits around Saturn, 9 billion miles traveled, liquid methane seas confirmed on Titan, geysers of water discovered erupting from the south pole of Enceladus, the building blocks of life detected inside those geysers, Saturn's magnetic field mapped with unprecedented precision, and in the final weeks of its existence, during what NASA called the grand finale, 22 passes through a region of space no human-made object had ever entered, the 100 to 100-mile gap between Saturn's innermost ring and the top of its atmosphere. Scientists had no certainty the spacecraft would survive those passes. They flew it through anyway, instruments running at full capacity, sensors wide open, collecting data from a place that had never been measured from the inside. The final images were transmitted on September 13th, 2017. 2 days later, Cassini entered Saturn's atmosphere at over 70,000 miles per hour and was gone. The data was archived. The mission was declared complete. The books were closed. And then, years later, researchers went back to those archives with better analytical tools and a deeper understanding of what they were looking at, and the books turned out to be anything but closed. Start with what Cassini's mass spectrometer measured when it flew through that ring atmosphere gap, because the numbers it returned were so unusual that scientists initially thought the equipment had malfunctioned. Complex organic compounds were raining down from Saturn's rings into its atmosphere, not simple molecules. Hydrocarbons, carbon-based chemistry, falling from the rings at a rate that, in the most conservative measurements from those final orbits, reached up to 10,000 tons of material every single second. Scientists already understood a phenomenon called ring rain, where particles from Saturn's rings trickle down toward the planet. But the scale Cassini measured in that final stretch was categorically different from anything prior estimates had suggested. The rings were not slowly leaking. They were actively pouring their contents into Saturn at a rate that means the entire ring system, the most iconic visual feature of our solar system, could disappear within 100 million years. Not billions, 100 million. On a cosmic timescale, that is not very long. The rings as we know them are not a permanent feature of Saturn's identity. They are a temporary chapter in a much longer story. And the clearest numerical evidence for that conclusion came from the final measurements a dead spacecraft took before it deliberately destroyed itself. The organic compounds were only the first thing hiding in those grand finale orbits. The second finding is the one that sent ripples through the physics community, because it challenges something more fundamental than ring dynamics. Saturn's magnetic field is aligned with its rotation axis to within 0.1 degrees. For comparison, Earth's magnetic north is offset from geographic north by roughly 11 degrees. Jupiter's field is tilted. Uranus and Neptune are dramatically offset. The universal observation across planetary science until Cassini measured Saturn's field with the precision of those final close passes was that a perfectly aligned magnetic field should not be able to sustain itself over billions of years. Standard models of planetary magnetic field generation, the same models that correctly predict the behavior of every other planet's field we have measured, require a tilt. A perfectly aligned field, according to the physics that explains everything else we have observed, should collapse. Yet Saturn's field sits there, impossibly stable, impossibly precise, measuring 0.1 degrees or less of tilt. Cassini's final dives gave science the most accurate measurement of this anomaly ever taken. and the anomaly only became more anomalous under that precision. Some researchers now propose there must be a hidden internal shell somewhere deep inside Saturn, a conducting layer that is canceling out what should be a tilted field before it reaches the surface. Others say our models of how planetary magnetic fields are generated are simply incomplete, and Saturn is telling us something about planetary physics we do not yet understand. Neither explanation has been confirmed. Both require rethinking what we thought we knew. Cassini handed science a puzzle with no current solution. The data supporting that puzzle came from the same final transmissions that detected organic compounds raining from the rings. Then, in December 2025, a paper published in the Planetary Science Journal extracted something that had been sitting unrecognized in the grand finale data for years. Saturn's rings, the flat disk of ice and rock that every photograph of Saturn shows, are not actually flat or contained. Cassini's cosmic dust analyzer, during those final 22 orbits, detected a vast invisible halo of dust particles extending up to 3 times Saturn's own radius above and below the ring plane, 3 times the planet's radius. The rings of Saturn are surrounded by a ghost-like cloud of material reaching into a region telescopes never had reason to look in, a structure so diffuse that it is invisible to remote observation and detectable only by a probe physically passing through it. Every image you have ever seen of Saturn, the one with the beautiful flat rings, represents an incomplete picture. The real Saturn is wrapped in an enormous dust envelope that extends to distances we did not account for, and we know this only because Cassini flew through the outer edges of it and recorded what it encountered before the mission ended. But none of the ring dynamics, the magnetic field anomaly, or the hidden dust halo compares in scientific and philosophical weight to what the Enceladus data revealed in October and November 2025. That is the discovery that changes the conversation, not just about Saturn, but about where life in the universe might be found. Enceladus is small enough to fit inside the continental United States. It orbits Saturn in less than 33 hours. When Cassini arrived at Saturn, Enceladus was considered a minor curiosity. By 2005, it was one of the most important objects in planetary science, after the spacecraft discovered enormous jets of water vapor and ice particles erupting from cracks in the moon's south polar region and shooting thousands of kilometers into space. Those geysers revealed a liquid water ocean beneath the ice, kept warm by the tidal forces Saturn exerts on the moon's interior as it orbits. Over the following years, Cassini flew through those plumes repeatedly, and each pass revealed more. Salt in the water, silica particles indicating hydrothermal vents on the ocean floor, the kind of structures that, on Earth, many scientists believe created conditions for the first life, simple organic molecules. Each discovery was significant. None of them prepared science for what came out of the archive in 2025. The key distinction that researcher Nozer Khawaja's team made in their October 2025 paper was one that had not been clearly made before. Most of the organic material identified in earlier analyses of Cassini's data came from ice grains circulating in Saturn's E-ring, grains that can be hundreds of years old by the time they were sampled and that have been altered by prolonged exposure to radiation in space. When Khawaja's team reanalyzed the freshest grain samples, the ones clearly ejected directly from the active geysers rather than from the aging ring population, using analytical methods more sophisticated than were available during Cassini's active mission, the results were qualitatively different from anything previously identified. The fresh plume material contained complex organic molecules that had never been identified in the older ring data: esters, ethers, alkenes, nitrogen, and oxygen-bearing compounds. On Earth, esters and ethers are not exotic space chemistry. They are components of lipids, the molecular family that forms the membranes of every living cell. They are part of the foundational structural toolkit of biology. Every cell in every organism on this planet has a membrane, and the chemistry underpinning those membranes belongs to the same molecular family that Cassini detected shooting from a liquid ocean beneath the ice of a moon orbiting Saturn. The paper was published in Nature Astronomy in November 2025. Co-author Frank Postberg, who has spent years working with Cassini's mass spectrometer data, stated directly that the complex organic molecules detected in Saturn's E-ring are not simply products of long exposure to space radiation acting on simple precursors. They are, in his words, readily available inside Enceladus's ocean. That sentence carries weight that deserves to sit for a moment. The ocean is actively producing these compounds right now. Whatever chemistry is occurring beneath that ice is not ancient and passive. It is ongoing, energetically driven, and producing molecular complexity at a level science did not expect to find 900 million miles from the sun. What kind of environment generates that chemistry? Consider what the hydrothermal vent evidence requires to be true. The silica particles Cassini detected in earlier mission passes are of a specific size and type that can only form when water at very high temperatures contacts silicate rock. That means hot water. Hot water means hydrothermal circulation. Hydrothermal circulation at the ocean floor of Enceladus means the boundary between water and rock on that moon is not cold and dead. It is geologically active, producing heat and driving chemical reactions in the water above it, exactly the way Earth's own hydrothermal vents drive chemistry at the bottom of the Pacific and Atlantic and Arctic Oceans. And the vents on Earth's ocean floor are not barren. They host ecosystems entirely independent of sunlight. Organisms that require no photosynthesis, no connection to the surface, no solar energy at all. Life built on the chemical energy released when hot water meets cold rock. Chemosynthesis rather than photosynthesis. That class of life, discovered on Earth in 1977, established that liquid water and chemical energy are sufficient conditions for biology. Sunlight is not required. The question of whether something similar could exist inside Enceladus is therefore not speculative in the way that question would have sounded before Cassini. It is a question with serious scientific weight behind it, supported by direct measurement of the relevant chemistry. While the Enceladus results were reshaping astrobiology, Cassini's Titan data was producing a correction of a different kind. For years, the assumption was that Titan almost certainly hosted a large subsurface ocean of liquid water, kept alive by internal heat and tidal activity from Saturn. In September 2025, a re-examination of orbital dynamics data from Cassini's Titan flybys suggested the moon's interior behaves differently than models predicted, and that the previously theorized massive water ocean is probably not there in the form scientists expected. That finding demonstrates the other dimension of what Cassini's legacy keeps delivering. Not just confirmations of what researchers hoped to find, but corrections to assumptions that had settled into scientific consensus. Science refining itself on the basis of better analysis of the same archived measurements, with the universe pushing back against the models built to explain it. And then there is Mimas, Saturn's small moon, famous for its enormous impact crater that makes it look unsettlingly like a certain fictional space station, was, until recently, considered one of the most geologically dead objects in the Saturn system. No internal heat, no signs of activity, a frozen, cratered ball of ice that appeared to have been cold and inert for billions of years. In early 2024, scientists analyzing Cassini's records of Mimas' orbital motion, the tiny precise variations in how the moon moves around Saturn, announced that the only explanation that fits the data is a liquid water ocean beneath the surface, one that formed somewhere between 5 and 15 million years ago, essentially newborn on geological timescales. The surface looks ancient. Nothing external suggests an active interior. But the orbital wobble Cassini recorded tells a different story that cannot be explained any other way. A hidden ocean inside a moon that looked like a dead rock, found not through direct sampling but through the patient mathematics of orbital dynamics recorded in archived data years before anyone knew what the data was going to reveal. This is the pattern that defines Cassini's continuing legacy. The spacecraft observed, recorded, and archived. Then science developed, understanding deepened. New analytical methods were developed. And researchers went back to the numbers and found things that were always there, invisible until the tools existed to recognize them. The hidden halo was in the dust analyzer data from 2017. The ester and ether chemistry was in the mass spectrometer records from plume flybys years before the 2025 paper was written. The Mimas ocean was in the orbital mechanics data. None of these findings required new observations. They required new understanding applied to old measurements. The full picture that emerges from Cassini's continuing legacy is one that no one predicted when the spacecraft launched in 1997. Multiple moons in the Saturn system have liquid water oceans beneath their surfaces, including at least one that shows absolutely no obvious external sign of internal activity. A planet's rings are actively dissolving into its atmosphere at a scale that will end the ring system within a geologically short time frame. A magnetic field exists in a configuration that standard physics says should not be stable, yet is. A dust halo surrounds the ring system at 3 times the planet's radius, invisible to telescopes and revealed only by direct passage through it. And from the south pole of a small frozen moon, an ocean is actively generating the molecular precursors of biology and shooting them into space through jets that a spacecraft flew through and analyzed and archived, and that researchers in 2025 finally had the tools to fully read. The European Space Agency has already designated Enceladus one of its highest priority targets for a future mission, studying a spacecraft that would sample the plume materials directly from the surface of the South Polar region. NASA's Europa Clipper is currently en route to Jupiter, applying the same ocean-moon investigation principles that Cassini developed. The field of astrobiology has been structurally reshaped by what Cassini found. Scientists now speak of a class of worlds called ocean worlds as serious candidates for life detection, with 5 of them in our outer solar system alone holding liquid water right now. Before Cassini, that conversation was theoretical. After Cassini, and especially after the 2025 and 2026 publications, it is evidential. Scientists estimate the full scientific yield of Cassini's data will take another decade to fully extract. Every year brings new papers. Every new paper brings something that was hiding in numbers collected by a machine that no longer exists. The spacecraft burned alive in Saturn's atmosphere on September 15, 2017. Its last signal reached Earth 83 minutes after the probe itself had ceased to exist, because that is how long light takes to travel from Saturn. For 83 minutes, Cassini was already gone and nobody on Earth knew it yet. The data was still flowing. The voice was still being heard, and in a real sense, that voice is still being heard now. Not in radio transmissions, but in the patient, careful, years-long work of researchers, applying new understanding to archived numbers and finding things that were always there, waiting for science to become ready to read them. The final images did not close the story. They started a new one. And what that story is saying about complex chemistry and hidden oceans, about the molecular foundations of life erupting from a frozen moon, about temporary rings and impossible magnetic fields and invisible dust halos, is more extraordinary than anything the scientists who built Cassini dared to hope they would find when they aimed it at Saturn in October of 1997 and let it go.